Hello friends, so we are into the second lecture of our week number 10 where we are talking about the measurement of temperature, and this is probably quite apt time of talking about this particular parameter, because as I have mentioned during the previous lecture, this is probably the most common parameter that not only engineering says but we also keep on using this in day to day life. The concept of temperature probably is known to even the anyone who doesn't have any relation with education at all, but also it is quite apt to discuss about this during this time of the course, because this is just the beginning of the summer. We are in the end of March, beginning of April, the temperature has started to rise up, the summer has officially begun, but in different parts of the country it has already touched 40 degrees Celsius. So that's why the temperature measurement has become more important as we keep on checking the daily weather reports. And what are the different ways of doing that we are learning in this particular week or this particular module. Now, in the previous lecture we have discussed about a few thermodynamic fundamentals about the measurement of temperature, or related to the measurement of temperature, the application of the second law of thermodynamics to define the thermodynamic temperature scale, and subsequently we have discussed about two different types of measurement of principles. One is based upon the expansion or volumetric expansion of some material, and the second one is based upon the change in pressure of some gas or vapor. Now, I was a bit down during the previous lecture. You may have noticed me doozing a bit also during the lecture, which was because of certain medical issues, but I hope I can keep it in a better shape in today's lecture. Now, during the previous lecture, two most important topics that we have discussed, which are related to the volumetric expansion. One is the use of bimetallic strips, and other is the most common temperature measurement in day to day life, that is the use of liquid in glass thermometer. Both are low accuracy, low cost devices, generally applied in situations where we are more looking for direct temperature measurement. That is, we need to take them in direct contact with the surface where we want the temperature measurement, and we are satisfied even if there is accuracy or inaccuracy of the order of 0.5 degree Celsius or 1 degree Celsius, because we are trying to get a rough idea about the exact level of temperature that we are looking for. While the liquid in glass thermometer finds its application in medical cases and also in several stationary devices where we generally want a permanent option of temperature measurement, the bimetallic strips are more used for certain kind of control applications, like we have briefly touched upon. It can be used as thermal switches. Very commonly you will find those kind of thermal switches, conventionally called the thermostats, in domestic refrigerators. Like as a temperature inside the freezing compartment or your refrigerator compartment goes below a certain temperature, the thermostat is set such that it disconnects the electrical circuit, thereby stopping the entire operation or electrical operation, stopping the compressor. And as the temperature inside the container or inside your refrigerator keeps on increasing, the bimetallic strip again starts coming back to its original shape, and beyond a certain temperature it again connects the circuit, thereby allowing the flow of current through it and again switching on the compressor. So, the thermostats can act as a switch on off kind of switches, or like we have mentioned about for compensation in clocks or in pendulum based watches, there also you can use thermostats. The thermometer, as we have mentioned, are more for domestic purposes. Before we move on to the other type of device measuring principles, let us solve a few numerical examples just to illustrate the concept that we have discussed in the previous lecture. The first one is related to a bimetallic strip. Please read the problem carefully. So, we have here an inverse brass combination based bimetallic strip. So, basically we are talking about a strip where we have an inverse slab and another brass slab, both are coupled with each other, fitted with each other, and their properties are different. Property values are not directly given here, but I have noted those properties. So, for inverse, the relevant properties are the Young's modulus, let us say we call it 1, which is 152 gigapascal, and alpha 1, that is a coefficient of thermal expansion or volumetric coefficient of thermal expansion, is given as 1.7 into 10 to the power minus 6 meter per degree Celsius. What about this unit? How this one is looking like, meter per degree Celsius? It suggests that if the initial length of the bar is 1 meter, then for 1 degree Celsius change in temperature, the change in length will be 1.7 into 10 to the power minus 6 meter. Similarly, for brass, corresponding Young's modulus E2 is 90 gigapascal, and alpha 2, the volumetric expansion coefficient, is 18.7 into 10 to the power minus 6, that is meter per degree Celsius. That is, for a brass bar of 1 meter length, we will experience a change in length of 18.7 micrometer for 1 degree Celsius change in temperature. So, they are having distinctly different values of this coefficient of volumetric expansion. Accordingly, there will be deflection with change in temperature. Let us say the top bar is 1, which is inward, the bottom bar is 2, which is brass. Now, from this value, can you tell if the temperature increases, then what will be the direction of the curvature, or in a better way, how the bar is going to, how this bimetallic strip is going to bend? Of course, brass is having higher coefficient of expansion, so the expansion of brass for a given temperature change will be more, and therefore, with increase in temperature, its shape will be something like this. This is for inward, and this is for brass. Brass being on the outer side, its length will be more, which is definitely the one that we need, corresponding to higher value of alpha. Similarly, if the temperature reduces, it will take a shape like this, with brass being on the inner side, because its contraction is more, inward remaining on the outer side. So, let us come back to the problem. We know the properties for both the corresponding material. It is given that the total thickness of the strip is 1 mm. So, this total thickness is this T equal to 1 mm, that is given. A length is 50 millimeter. So, this particular length L is 50 millimeter, width of 12 millimeter. The width is not shown here, that is a third dimension out of the, which is normal to this particular screen, and TA equal to TB, that is an important information. So, the thickness of both the materials, TA equal to TA and TB are equal, or let us just write this one to be consistent with the notation that you are using, say T1 equal to T2. Now, we have to estimate the end deflection for a temperature rise change of 30 degree Celsius, and if the end is held fixed, estimate corresponding force development. So, that is the second part. We shall be coming back to that after calculating the first part. So, just try to remember the relation of radius of curvature for a bimetallic strip that I have given in the previous lecture. So, if we take from there, here m, which is given as T2 upon T1. So, or we could have taken in any way. So, let us say m is equal to T1 upon T2, and that is equal to 1. N is equal to E1 upon E2, which is 152 by 90. So, how much is N? It is 1.688. Correspondingly, N plus 1 by N is equal to 1.688 plus 1 by 1.688 is equal to 2.28, which can roughly be taken equal to 2 for our purpose. You may doubt that 2.28 and 2 is significantly different, but there are certain situations where this value can be well beyond 2, and that is why around this range we can take it to be equal to 2. And when m equal to 1 and n plus 1 upon n equal to 2, then what is the relation corresponding to the rho, the radius of curvature? This relation, the simplified relation that we have used in the we have seen in the previous drill, it is 2t divided by 3 into alpha 1 minus alpha 2 into delta t, or T2 minus T1. So, this is a simplified relation for the case when m equal to 1 and n upon 1 plus n is equal to 2. And just note one thing here, we have taken M and N definition with T1 by T2 and E1 by E2, that is we are taking the properties of inverter in the numerator and brass in the denominator. Now, as long as we are dealing with this situation, M equal to 1 and N plus 1 upon N equal to 2, it does not matter which order we are taking, because when TA and TB, or sorry, the T1 and T2 are equal, M will always be equal to 1 depending on independent of whether you are defining it at T1 upon T2 or T2 upon T1. Similarly, here we are taking N plus 1 upon N. So, this practically always is E1 upon E2 plus E2 upon E1. So, again the definition of N is immaterial in this case. However, if we are made to make use of the full relation, then the order is important, because that will designate the direction of deflection. So, the value of rho is here. Let us put the numbers. So, we have 2 into T, the thickness is 1 millimeter. So, 1 into 10 to the power minus 3. I keep on repeating, always use the SI units. So, we have converted this millimeter to meter to make the calculation consistent, divided by 3 into alpha 1 minus alpha 2. So, here alpha 1 is 1.7 minus 18.7 into 10 to the power minus 6 into delta T is 30. Now, here as we have written alpha 1 minus alpha 2, so we are getting a negative sign, but we are generally interested with the absolute value of rho. So, that will be coming to be equal to 1.3072 millimeter, oh sorry, 3072 meter. Again I have pre-calculated the numbers for solving the problem, but we have to calculate the deflection of the end of the bar. So, let us say this was the initial bar, which is given by a vertical line, and after the deflection it is like this. So, this is the deflection that has taken place and given by the angle theta. Then this particular situation or this particular length is this radius of curvature that we are talking about, and this is the deflection that we are talking about y. This particular length is L, the length of this bar. So, what is the relation between theta and rho? So, we can roughly write theta, as long as this theta is small, is equal to L upon rho. Now, length of this is 50 millimeter, 50 into 10 to the power minus 3, by rho we have just calculated 1.3072. So, we are getting this one to be 0.038 radians, and once we have got that, then y can, the deflection y can roughly be taken as rho into 1 minus cos of theta from this trigonometric portion, where y is the one that we are looking for. So, putting the number, rho we have calculated to be 1.3072 into 1 minus cos of 0.038. Putting the values, we are having a deflection of 0.956 millimeter. So, the total deflection that is taking place is equal to 0.956 millimeter, or approximately 1 millimeter, which is extremely small deflection, but with a suitable deflection measuring instrument, suitable strain gauge kind of device, we can easily detect such a deflection to, and then subsequently that can be related to the corresponding temperature change of 30 degrees Celsius. So, this is the first result. Now, the second part is saying that if the end is held fixed, estimate the corresponding force development. So, you have to calculate the force if this end is kept fixed, that is the strip is not allowed to expand freely. To identify that, we can make use of the standard relation for a cantilever kind of bar, means here one end is kept fixed. In that case, this is the standard cantilever formula from the concept of engineering mechanics we can make use of. Y equal to FL cube divided by 3 EI, which is standard formula for any cantilever. F is the force that we are trying to estimate. So, F is equal to 3 EI y divided by L cube. Now, the question is, what is I? I for a rectangular strip, it is BT cube by 12. that is the thickness is given as 12 millimeter, 12 into 10 to the power minus 3 into and the thickness is 1 millimeter, 1 into 10 to the power minus 3 whole cube divided by 12. So, 12 cancels out and we are getting this to be 10 to the power minus 12 millimeter to the power 10 to the minus 12 meter to the power 4. So, if we put it back here, then corresponding value of force is coming to be something like 2.88 Newton. So, this is the second result that we are looking for. This is the amount of force that will get produced if one end is held fixed for this. Of course, all these results depend upon the value of the delta T. These are two numbers correspond to 30 degree Celsius. If we suppose trying to solve the same thing corresponding to delta T equal to 60 degree Celsius, then your y will be much larger. Your y will be something like 1.91 millimeter and corresponding force will be significantly larger, 5.55 Newton. So, both are nearly double corresponding to the previous value, and that is expected also because the way you are solving this, we have almost linearized the relation between delta T and y. Now, this is a problem in relation with the bimetallic strip. Let us try to solve another numerical problem involving the liquid in glass thermometer. To TIG, it should not be TIG, it is a typing error, it should be LIG. Liquid in glass thermometer are made of identical material and employ mercury as the working fluid. So, we are talking about two mercury thermometer, both are made of identical materials. Both are accurately calibrated at 0 degree Celsius and 100 degree Celsius. So, on both the thermometers, the position of mercury column or I should say the position of the tip of the mercury column at 0 degree Celsius and the position of the tip of the mercury column at 100 degree Celsius have been accurately identified, but it has not been calibrated for any of the intermediate points. Now, one has a tube of constant diameter. So, first thermometer has a tube of constant diameter and the other has a tube of conical bore 10% greater in diameter at 100 degree Celsius position compared to 0 degree Celsius position. So, there is a difference between the two thermometers. If we roughly draw them, one thermometer has a constant diameter. So, let us say this is the 0 degree Celsius portion and this is the 100 degree Celsius portion, both have been accurately identified on this thermometer. And the other thermometer is having a conical kind of shape, where again this is the 0 degree Celsius position, this is the 100 degree Celsius position and these two are also correct position, but the area in the second thermometer keeps on changing as the temperature reading keeps on increasing. Now, if the distance between the two extreme points are uniformly subdivided in both thermometers, so in both the cases all the 100 divisions between 0 to 100 are taken to be uniform, which definitely seems erroneous for the second case. For the first case, as the diameter is uniform, so an uniform subdivision is justified. However, for the second case, as the diameter keeps on increasing as we are moving in the upward direction, the distance between subsequent temperature readings or the width of each subdivision corresponding to 1 degree Celsius can't be the same, but in this case it has been done. So, the question is what will be the reading of the straight bore thermometer in a place where the other reads 50 degree Celsius. That means, the second thermometer, that is which is the one having a conical bore, has been taken to a place where it is showing 50 degree Celsius. Now, as per the design, the 50 degree Celsius position should lie exactly in the middle portion of these two 0 and 100, as it has been uniformly subdivided. However, as we know the diameter is changing, so that actually is an erroneous position. Then the question is what is the correct temperature there, which you can measure using the straight bore thermometer. Now, we know that for any such device, the volume of mercury at temperature T can be given as V naught into 1 plus beta into T minus T naught, where T naught is some reference temperature, V naught is the volume corresponding to that, or volume of mercury corresponding to the temperature T naught, and beta is the coefficient of volumetric expansion. Vt is the temperature corresponding to this T. Let me use capital T to be consistent. So, Vt minus V naught is equal to beta V naught into T minus T naught. So, let us say we take T naught equal to 0 degree Celsius, then the volume of mercury or the change in volume. So, this V T minus V naught can be also written as delta V corresponding to 0 to T. So, delta V corresponding to a change in temperature from 0 to 100, that should be how much? That should be equal to beta V naught into 100 minus 0. Similarly, the change in volume when the temperature changes from 0 to 50, then it should be beta V naught into 50 minus 0. If we combine these two, then change in volume for temperature change from 0 to 50 divided by the change in volume corresponding to the 100 degree Celsius temperature change should be equal to 50 by 100, that is equal to half. So, had we measured with the had measured with the straight bore thermometer, then the 50 degree reading should have appeared exactly at the middle. But as the volume of the or I should say the cross section area keeps on changing in the conical bore thermometer, this if this 50 degree which is erroneously marked exactly the middle position, that is not correct, that we have to rectify now. So, how can we relate them? To solve this, let us expand this conical thermometer to form an hypothetical conic. Let us say this point is 0. Let me remove this. Let us say this is A, this is B. The thermometer is showing 50 degree reading. So, correspondingly it is C, it is D, it is E, and this is F. So, when it is showing the reading of 50 degree, the mercury tip is appearing along the line CD. Let us mark this particular distance, say as L prime, the distance below AB, and we are marking this particular distance as L. So, L prime divided by L plus L prime, that should be what? Following the property of the cone, this cone where the diameter is changing consistently. So, we can write L prime to be equal to D, where D refers to the distance at this position, and how much is the distance at this position then? D refers to the diameter at the 100 degree at the 0 degree Celsius position. Then at the 100 degree Celsius position, that is at EF, how much should be the diameter? It is given that the diameter is 10% greater. So, it should be 1.1 times D. So, it is 1.1 times D. So, if we make use of this, 1.1 L prime is equal to L plus L prime. So, from there L prime is equal to 10 of L. Similarly, if we make use of the CD position, now as the thermometer has given uniform subdivision, so this height should be L by 2 because it has been uniformly divided. So, L prime divided by L by 2 plus L prime, how much that should be? At L prime position diameter is D, at L by 2 plus L prime position diameter is CD, let us say. So, L prime into CD is equal to L by 2 into D plus L prime times D. From there, if we use the definition of L prime, so we know that we can write CD is equal to L by 2 into D plus L prime into D divided by L prime, and L prime we have identified to be 10 L. So, if we put that, we have L by 2 plus 10 L by 10 L into D. So, 10.5, that is 1.05 D. So, the diameter at this particular position is 1.05 times the diameter at the 0 degree position, which is logical also, because again the cross section area is changing uniformly. as it is changing by 10% at the 100 degree position. So, it should change by 5% in the 0 degree position. Now, delta V corresponding to 0 to 100 position, how much is that, which is we have identified to be as beta V naught into the change in volume from 0 to 100, that volume, and similarly delta V naught 0 to 50 or corresponding to any temperature T should be beta V naught into T. So, if we take a ratio of these two, delta V naught corresponding to 0 to any temperature T by delta V corresponding to 0 to 100 is equal to T upon 100. Now, corresponding to T, the volume is at 0 degree. Let me remove this marks because it is looking quite. So, this is your 0 degree position A, B. So, at 0 degree position, when the temperature is 0 degree Celsius, mercury is occupying this particular volume. When it is showing this 50 degree position, so the change is this particular amount, and when the change it is moving to the 100 degree position, the change is taking place, which is the second hashed area plus the one that is left. So, the total area corresponding to this should be the volume ACDB divided by the volume when the expansion is taking from 0 to 100 should be equal to AEFB, that is equal to T by 100. So, now how much is this volume ACDB? ACDB volume should be the volume of the cone 0 CD minus the volume of the cone 0 AB divided by the volume AEFB, which is the volume of the cone 0 EF or OEF minus the volume of the cone OAB. So, if you use the for corresponding relations, so it will be equal to 1/3 into pi by 4. So, ACDB, that is CD square, which is 1.05 D whole square, into corresponding length. How much is the corresponding length? We have identified the corresponding length to be 10.5 times L minus the 1/3 pi by 4 D square into 10 L divided by 1/3 pi by 4 into 1.1 D whole square into 11 L minus 1/3 pi by 4 D square into 10 L equal to T by 100. L and D square cancels out, pi by 4 cancels out, 1 by 3 also cancels out. So, it reduces to 1.05 square into 10.5 minus 10 divided by 1.1 square into 11 minus 10 equal to T by 100, and if we solve this, now T will be coming to be something like 47.7 degree Celsius. So, your conical thermometer is showing 50 degree, but actual temperature is about 48 degree Celsius, which we can get using the relation like this, consistent volumetric expansion of the thermometer or mercury inside the thermometer. So, that is the way we can make use of the concept of volumetric expansion of either solid in case of bimetallic strips or liquid in case of liquid in glass thermometer to get quite easy measurement of temperature. Let us move to a different category of devices which is based upon the changes in electrical properties. These are extremely popular devices for temperature measurement in different industrial applications, and there are several varieties of that also. And the first one is called the resistance temperature detector, or in short, taking the first 3 letters is called RTD. Extremely popular name, resistance temperature detector or RTD. In certain literature it is also called the resistance based thermal detector or thermal detection. So, the idea is very simple. As the temperature changes, you know that the value of resistance of any common conductor that also keeps on changing, and the same property is made use of in this device. Here the RTD is nothing but a resistor, generally in the form of a thin wire or maybe in the form of a metallic film. As the temperature changes, its resistance also changes, and this RTD is commonly put as a part of a bridge circuit, which is normally in the null position, and as the temperature as when the RTD comes in contact with the location where you want the temperature measurement, there is a change in the resistance value. Accordingly, there will be a deflection or some voltage current start flowing through the circuit, thereby giving some voltage measurement, which can be sensed by the corresponding differential voltmeter. Now, this circuit can operate, or this voltmeter can operate either in the deflection mode, just to indicate how much deflection has taken place, or in the null mode, where we get the bridge back into the null position and correspondingly try to calculate how much effort we have to put in to get this null position. Either of that can give you a measurement about the change in resistor, and that can be related to the value of the corresponding temperature, because we commonly know that the resistors or value of resistance of any common conductor can generally be written as something like this: R naught into 1 plus A into T minus T naught plus B into T minus T naught square, plus we may have higher terms, but practical purposes generally do not go to this. We generally limit ourselves only to this second order term or the quadratic factor, where this T naught generally refers to the reference temperature, which is commonly taken to be 25 degree Celsius. R naught is the value of the resistance at the temperature T naught. If we take T naught equal to 25 degree Celsius, then this R naught is often referred as R 25 to indicate that the reference temperature is 25. Now, this once we know the value of this A and B for any given conductor, then just from the measurement of this value of this RT, we can calculate the corresponding value of the temperature T. For certain materials over a smaller temperature range, we can get an even simpler relation, where it can be just a linear function R naught plus A into T minus T naught, but generally this kind of relation is valid only over a small range, when the variation in temperature is limited only to something like 50 degree Celsius around that T naught. Certain materials like platinum can have this kind of linear relationship over a small temperature range, but if we are looking for a large change in temperature from the T naught, then we have to go by this kind of quadratic relation with the knowledge of A and B. Thankfully, we know the resistance characteristics of several common metals, and therefore, we know the values of corresponding A and B, which may also change with temperature, but we have significant database to know about the such variation, and so RTD becomes a very good device or very popular device for temperature measurement. These are some of the common materials and their resistance behavior. You can see platinum is having a quite linear profile. The resistance is changing here. Look at this, here we have plotted just RT upon R naught, and temperature, of course, in this graph the 0 degree Celsius is shown as the reference, but commonly we take 25 degree Celsius. Now, at the reference temperature, the value of RT is equal to R naught, so the ratio is 1. However, as the temperature keeps on increasing, its resistance also keeps on increasing. For platinum, it is nearly a linear profile. However, that may not be the case with copper, nickel and several other materials. Sometimes we may like to calculate the corresponding coefficient of temperature rise. For that purpose, we have to differentiate this expression in terms of temperature, which is, and then we shall be dividing this divide the value of R naught. This is called the temperature coefficient of resistance, or just temperature coefficient. Now, this most of the common materials like the metals shown here, they all have positive value of these resistance coefficients. Therefore, with increase in temperature, the value of the resistance also keeps on increasing. These are some of the common materials, their temperature coefficient of resistance is given. You can see the first one in the first column, it is given as a relative conductivity with taking copper as 100%. So, others like gold has quite high conductivity with respect to copper, silver can have higher than copper. However, certain materials like platinum etc. can have much lower, but the temperature coefficient of resistivity values is quite close to each other. look at the unit ohm per degree Celsius, which refers to the change in the resistance when the initial value of the resistor is 1 ohm and the corresponding change in temperature is just 1 degree Celsius, then whatever we are getting, that is temperature coefficient of resistance, which is this particular factor only. So, for several combinations like for copper, platinum, silver, it is around 0.0038 or 39. For gold it is 0034. However, something like iron or nickel, it can be quite high, 0.006. So, there is larger change in the coefficient, which is proven by the steep slope in this particular curve. Physically, an RTD sensor may look something like this, where we can have the resistance wire wrapped inside stainless steel sheet or stainless steel well, and the wires are separated from each other by insulating materials. We generally want their quite high coefficient of this resistance, thermal coefficient of resistance from this wire, and there are several other properties also which are desirable for a common conductor to be considered while fabricating an RTD. Some of the relevant properties can be the resistance should be suitable so that we can maintain a convenient size. Like we want a reasonable value of resistance within a smaller size. If the value of the resistance is small, then we need to have a very large value of the corresponding conductor, which may not be suitable for application. So, we want high resistance so that it is suitable to maintain a convenient size of the instrument. High thermal coefficient of resistivity definitely is desirable, so that for every small change in temperature we can have a large change in the resistance, leading to significant change in the voltage output from the bridge circuit, and hence a high sensitivity. Constant thermal coefficient of resistivity, that is also very important, as long as, like we have seen from the graph, for platinum it gives reasonably constant value of thermal coefficient of resistivity, so that resistance changes following a straight line with temperature or near straight line. However, that was not the case with nickel and copper. Now, if the coefficient of resistivity or thermal coefficient of resistance is not constant, then we are not going to get a linear scale. Only if it is a constant, then you can get a linear scale, which is possible for platinum over a smaller temperature range. It is for other materials we generally, or for larger temperature change, we generally get a non-linear scale. Corrosion resistance, there has to be wide temperature range as solid. They should not get oxidized, and also it should maintain the solid state to over a large temperature range. And the residual strength should be also minimum, so that we can get a high reproducibility and quite reasonably fast response from the device. Considering these factors, there are several materials which can be considered while making RTD. Platinum remains the most common choice. Platinum is costly, but it provides, as I have mentioned, it provides a highly linear response, and also it has good corrosion protection characteristics, and that is why platinum is generally used for several applications involving the calibration standards also. Tungsten is another material which also gives reasonably good linear response. Copper is cheap, but copper has a highly nonlinear behavior, and the temperature range available for copper is also quite low. Similarly, nickel, the cost is low, but it is nonlinear, and the corresponding low temperature range can be another problem with nickel. Though nickel has very high thermal coefficient of resistivity, so its sensitivity is very high, but the temperature range is a big problem with nickel. Sometimes we produce certain alloys of nickel which can provide some solution to this temperature range issue, but pure nickel generally has a much lower temperature range compared to platinum or tungsten. RTD remains probably the most common measuring instrument. If we are temperature measuring instrument, if we are looking for high level of accuracy, because it provides numerous advantages, something like wide operating range. Of course, we are not talking about the same device, but combining several devices, we can go for a wide range, something in the range of -250, -260 degrees Celsius to 1000 degrees Celsius, which covers most of the industrial applications that we can think about. High sensitivity for certain materials like nickel, etc. High accuracy as well. Accuracy can be in the range of 0.1 degree Celsius or even less. Near linear scale for material like platinum. Low resistance, 100 to 1000 ohm resistance it can provide, and therefore, we can have convenient size of the device within a what I should say, within a reasonable size of the resistor. Then high repeatability and stability generally we can get from RTDs, they are metal, so there is very less residual strain, and they can come back to their initial position quite quickly, or initial resistance value they can recover quite quickly. Low drift, thereby they can there is no need to have repeated calibration for them, and also generally they are corrosion resistance, which are some of the desirable properties as well. But there are issues also with RTD, like they are expensive, that is the first consideration, because we are thinking about materials like platinum or tungsten to make them, which are costly materials. Lead wear resistance can be significant, I shall be coming to this very shortly. Power source is required, we need a voltage source to activate the bridge circuit, whatever mode we are working, deflection or null, but the power source will be required. Response is slower because the resistance requires certain finite amount of time to get the modified value, and accordingly the bridge circuit requires certain time to respond. They can be fragile because we are generally talking about very thin wire, platinum wires, etc. So, if we are using them in some harsh environment, there may be maintenance issues. They can be sensitive to shock and vibration, which can be advantageous in certain situations but generally a disadvantage. And another big problem is the internal heating, because as the resistance current is flowing through the resistors, we can have I square or R heating loss. So, internal heating loss definitely is there, but another big error comes from the lead wear resistance. Lead wear resistance refers to the heating loss incurred by the long wires which are connecting the bridge with the RTD sensor itself. As it is quite sensitive to surrounding temperature, it can pick up the temperature of the surrounding, and accordingly can lead to significant amount of I square R loss. This is the one that is generally called a two-wire configuration, which is the general configuration, where we are connecting the actual resistance with these two resistance L1 and L2. Now, this is a situation where we can have significant I square R loss while the current passes through these two resistor L1 and L2. To remove that, we can try a 3-wire or 4-wire design. This is a 3-wire design where you can see L1 and L3 are the one which are connecting the resistor, and L2 is some kind of potential lead. Here they are designed such that commonly the resistor of L1 is equal to the resistance corresponding to L3, so that they can cancel the lead error issue and give a stable response. And it is generally designed such that R3 is equal to the resistance of the conductor or actual sensor. Thereby we can maintain at least at the beginning, because I should say this is RT0, R3 should be equal to RT0. In that case, we can maintain a 0 output voltage to start with, and then as R3 is not changing, L1 and L3 may change, but their effect cancels each other. So, only change that is happening is this RT, and accordingly we can get the corresponding output. This C is a even better configuration, it is called a 4-wire configuration, definitely more expensive, more complicated, because we have to include 4 resistors, but this is the optimum configuration. In constant current flows through this L1 and L3, whereas L1 and L4 and L2 and L3 are connected with the actual sensor to give the corresponding output voltage. Their lead wear effect of L1 is cancelled by L4, lead wear effect of L2 is being cancelled by L3. So, a highly stable response we can get from them without too much leading error. So, these are the resistance temperature detectors or RTDs. But there is another kind of resistance based temperature device which is called thermistor. Thermistor are semiconductor based devices and its operating principle is just opposite to the RTDs. Thermistors generally are made of devices which are having negative temperature coefficient of resistance. The RTD materials generally have a positive temperature coefficient, so that with increasing temperature their resistance increases. But thermistors are made of semiconductor devices whose resistance decreases. Just look at this graph. Here we have represented 3 thermistors A, B and C. The first one A is having a resistance of 100 ohm at 25 degrees Celsius, and as the temperature changes you can see there is a sharp reduction in its resistance value. Just when it reaches around 50 degrees Celsius, while it is 100 ohm around 0 degrees Celsius, it is more than 300 ohm at 0 degrees Celsius, as it is 100 ohm at 25 degrees Celsius, it is more than 300 degrees Celsius at 0 degrees Celsius, whereas it is quite small, maybe in the range of 30 ohm or something at 50 degrees Celsius. So, there is a significantly sharp change. Look at the other two. In case of B, the initial resistance or at 25 degrees Celsius, the resistance is 1 kilo ohm, that is this particular value, and correspondingly observe how much is the change. When you reach 100 degrees Celsius, corresponding resistance value has dropped to well below 100. That is a significant change. Same for C. Now, if we compare that to a standard RTD material which is platinum, platinum at 100 ohm at 0 degrees Celsius, and look at how much is the change. When you reach 100 degrees Celsius, corresponding value may have changed only to 130 or 140 ohm. So, much smaller change in temperature that we are seeing here in case of RTD materials, but thermistors are having significantly higher value magnitude of this temperature coefficient of resistance, and that is why they can give extremely high sensitivity. Commonly their resistance can be represented by a relation something like this, R naught into exponential beta into 1 upon T minus 1 upon T naught, where beta is some coefficient, R naught is the value of the resistance at temperature T naught. The value of beta can be practically very high, in the range of 1000 to 5000 Kelvin inverse. So, the significantly high sensitivity that we are talking about. If we are interested in the value expression for temperature alone, then we can write this way: RT by R naught is equal to exponential of beta into 1 by T minus 1 by T naught. So, T minus 1 by T naught is equal to 1 by beta into ln of RT upon R naught, that is 1 by T is equal to plus 1 by T naught. So, sorry, in the left hand side it should be 1 upon T, because T naught we have taken on the other side. So, we are getting it to be beta plus T naught into ln RT by R naught. From there T is equal to beta T naught divided by beta plus T naught into ln RT upon R naught. So, once we know the value of the RT at the modified temperature, we can easily get the value of temperature from the knowledge of T naught and beta. This is the working principle of thermistor. Thermistors are semiconductor devices, as I have mentioned. They generally can be oxides of manganese, nickel, cobalt, etc., which can have very high resistivity, and corresponding thermal resistance also can be much higher. Like as we have seen, the RTD materials generally have lower resistance in the range of 100 ohm to 1 kilo ohm, whereas for thermistors the resistance can be significantly higher. And so, we are talking about resistance in the range of 100 ohm to something in the range of 400 kilo ohm. So, they start with much higher resistance, and as the temperature changes the resistance drops quite sharply, as characterized by this particular beta value. Certain material like doped germanium, impregnated glass, etc., can also be used in cryogenic application as common materials for this. Their advantages are they are much cheaper than RTD, they have very high accuracy and very high sensitivity, much higher than the RTD. like if we compare, just look at the expression, the sensitivity expressions we have seen, the rate of change of temperature, resistance with temperature divided by the initial resistance value. So, from this particular relation, if we compare say at 25 degree Celsius, the value for this sensitivity for a platinum resistor can be in the range of 0.003 or 0.038 as we have seen, whereas in this case for a standard thermistor it can be minus 0.045. So, it is at least 10 to 15 times, sorry 11 to 15 times larger sensitivity that we are talking about. That is why they can sense extremely small changes in temperature as well. They can act as a compensator in circuit, because most of the common material generally have an increase in resistance with increase in temperature, but thermistors have a decrease in resistance. So, they often can act as the compensator in common circuitry. The operating circuitry or electrical circuitry also becomes much smaller, like they do not have any kind of lead wire issue, lead wire error kind of issues. So, we do not need any additional resistors, entire thing is much simpler. In fact, we can go for very simple ohm meter kind of application or kind of circuit, or we may have simple ballast circuit, we may have bridge kind of configuration in either deflection or null mode. We can also have certain times special linearizing circuits, so that we can get voltage as a linear output function of the change in temperature. There are several options we can have with in terms of the corresponding circuit. High resistance, as I have just mentioned, 1 to 100 kilo ohm, actually I have mentioned about 400 or 500 kilo ohm also. So, the size of the resistor is, or size of the thermistor sensor is extremely small, very small resistance to start with, and with a very small dimension we can get the required level of resistance to start with. We do not need any additional transmitter, like in case of RTD we may need. Small physical size because of the high resistance, and therefore, they have much faster response compared to RTDs. High resolution, and can also be used for control, temperature control or several other purposes as well. Like thermistors can also be used for measurements of parameters like pressure, power. They can be also used for temperature control, sometimes as heat flux sensors, sometimes as overload protection purpose, warning symbols or warning signs, etc. There are numerous kind of applications, downstream application we can have for thermistors. Certain issues definitely it will be having: smaller temperature range compared to RTD, like minus 100 to 300 degree Celsius. So, we are talking about a temperature range of only about 300-400 degree Celsius, whereas for standard RTDs can cover something above 1000 degree Celsius. So, it is one big concern for thermistor. One single device can't give you beyond 250-300 degree Celsius temperature range. Nonlinear response because of the exponential relationship with temperature, more susceptible to self-heating compared to RTDs, very sensitive to ambient temperature because of their high sensitivity. That is one downside of having high sensitivity, and less stable because semiconductor material can have hysteresis effects also. So, these are the issues that you need to be careful of while dealing with thermistors. Thermistors can be fabricated in different shapes, like we can have glass coated bead kind of structure, we may have chip kind of structure. They can also be fabricated in disc shape, or sometimes just flat axial plates like this, depending upon what kind of application we are going for. And finally, before I close the thermistor part, thermistors commonly we talk about materials having negative temperature coefficient, but actually there can also be materials which can have positive temperature coefficient, or thermistors which can have positive temperature coefficient. Certain semiconductor material which involves barium titanate can have quite high positive temperature coefficient, just like shown here. Sometimes heavily doped silicon can also act like this. Just check, initially for lower temperatures it is actually having a quite moderate negative temperature coefficient, but beyond a limit something like this, when it reaches the minimum resistance it keeps on increasing, and beyond a certain threshold or critical temperature there is a rapid increase in the corresponding resistance value. For this purpose, often these PTCs, PTC refer to positive temperature coefficient based material or materials having positive temperature coefficient. These PTC based thermistors can often be used as switching devices beyond a thermal switch, like when the temperature crosses or is lower than this limit, the switch will be remaining as say in open position. Now suddenly as the temperature, this particular temperature is crossed, this particular threshold is crossed, resistance will increase infinitely, almost infinitely, and thereby causing the circuit to stop. So this kind of thermal switch application and sometimes control switching application can be achieved with this thermistor having positive temperature coefficient. But commonly for temperature measurement or control purpose, we prefer to use the materials with negative temperature coefficient. The next material that I have in this category of changes in electrical properties is probably the most common way of temperature measurement in industries, which is thermocouple. The working principle of thermocouple is related to a very well known phenomenon in physics, that is the Seebeck effect. I am sure all of you know Seebeck effect. When two dissimilar materials are connected such that one end of the couple is maintained at a higher temperature and other end is maintained at lower temperature, then the current starts flowing through this, or in a way you can say that an electromotive force or EMF is generated at the other end if the ends are at dissimilar temperatures, which is called the Seebeck effect. The working principle of thermocouple is the same. We take two dissimilar materials, we connect them just this way. One end of the couple is kept at the position where we want to have the temperature measurement, and other end is the position where we can take the, or we can measure the corresponding EMF generated, and that EMF has to be a function of the temperature of the other end. So by suitable calculations, we can easily relate the EMF to the temperature, thereby getting a simple temperature measurement. And that is why thermocouples are extremely popular, because you can just take two wires of two corresponding materials or suitable materials, and now connect the one end of the two wires by any common method, bridging, soldering, or just tie them with each other, and now taking them in contact with a maybe a high temperature surface, you will immediately get an EMF at the other end. And once you measure that EMF, you can, using some calibration charts etc., you can easily get the direct value of the corresponding temperature. The Seebeck effect is of a material is generally measured in terms of something known as the Seebeck coefficient. Seebeck coefficient sigma t is generally defined as the potential the gradient of this potential developed with temperature, or we can also write at a given temperature this E sigma t will be of course sigma t dt over a range of temperature plus some constant C. Now this constant can be made to 0 by suitable choice of material and suitable choice of this reference temperature. So if we are dealing with a homogeneous material, then we can easily go for this E sigma t as something like if the change in temperature, some homogeneous material is going for temperature change from T1 to T2, or one end is kept at a temperature T1, other end is kept at temperature T2, then we can easily write this one as E sigma corresponding to T2 minus E sigma corresponding to T1. But sometimes we are dealing with, or most often we are dealing with non-homogeneous material where this E sigma is a function of not only temperature but the position as well. In that case, sigma becomes a function of both T and X, and hence E sigma is also a function of T and X, depends on which location we are measuring the EMF. So accordingly we can have it as x1 to x2 sigma xt dt dx. So the temperature gradients also comes into equation to deal with. These are certain common materials. You can see certain materials having a positive value of the Seebeck coefficients, whereas material like platinum or palladium are having negative value of coefficients. So we generally prefer taking one material from this side and another material from this side, and as soon as we connect them, we are going to get that EMF generated, thereby providing a thermocouple. The end of the thermocouple, as I have mentioned, we can connect them in different ways, just make a tip, or we can cover the tip with a cap kind of thing. The electrodes can be covered with the metal sheet, which can be grounded or which can be ungrounded as well, giving you a very simple configuration. This is the end where we generally have a bead here at the which will be taken to a point where you want the temperature measurement, and this particular end will be connected to certain temperature measuring device. So, thermocouples are cheap and simple, can provide very fast response because they are very small in dimension. The bead, point temperature sensing, which is not possible with any of the ones that we have discussed earlier. Wide temperature range can be covered with suitable choice of this material couple. No external power requirement like in case of RTDs or thermistors. They can provide decent accuracy, of course lesser compared to RTDs and thermistors, but still quite workable, definitely better than the expansion based devices. Rugged and durable, and no lead wear issues as well, but they also suffer from issues such as the susceptible to drift over time, extremely small output. So, we need to go for certain kind of magnification, because the EMF that we get, that quite often in the range of millivolts, just 5 or 10 millivolt range. So, we have to go for some kind of amplification to get a proper output signal. Less accurate than RTD and thermistor, susceptible to electromagnetic interference, as it is an electromagnetic phenomena that is going on. So, such kind of interference is possible if in the neighborhood some electromagnetic device is kept. Nonlinear output, and there can be corrosion issues as well, thereby the bead needs to be inspected very regularly. There can be different types of combinations of thermocouples as shown in this case. Most common ones are like called the T-type thermocouple, which is made of copper and constantine. Constantine is actually an alloy which has 55% copper and 45% nickel. It acts as the negative material, copper acts as the positive material, and one important thing is the outside jacket color. Just from like in the previous slide we have seen, the here we have two wires, and these are the two wires put inside this jacket. Here the jacket is of color blue, and from that color itself you can immediately identify which type of thermocouple it is. Like J-type thermocouples are having this blue color, so the one that was shown there is a J-type thermocouple. Another very popular one is this K-type thermocouple. Here we use two alloys, chromel, which is actually a combination of 90% nickel and 10% chromium, that is as the positive one, and alumel, which contains 95% nickel, 2% manganese, and rest as aluminum, that as the negative material, and the outside color is yellow. So, these are probably two most used thermocouples. J is also used. In case of J, you have iron on one side and constantine, which is an alloy of copper and nickel as the negative material. It has a black cover. So, others generally are used in different other purposes, like this are platinum or tungsten based things which are used for high temperature measurement, and also limited to precise use or very accurate use, because they are much expensive compared to the T or J type thermocouples. These are the response. As you can see, the E type thermocouple has the highest sensitivity. J, K or T type thermocouples also have quite good sensitivity compared to this R, S or C kind of thermocouples. Like just summary of the tables that shown here, T type is a copper constantine thermocouple, J is iron constantine, K is chromel alumel, and E is chromel constantine. These are generally the most popular 4 types of thermocouples used in industries, but their temperature range is important. Depending on which range you are going to work on, you will be choosing the corresponding thermocouple. Like T type thermocouple has a maximum temperature of plus 350, but lower side it can have minus 200 degree, whereas chromel alumel is generally used in higher temperature cases, though it can go to minus 200, but we generally use this one when the temperature is beyond the scope of T type thermocouples, like we are going in the range of 300 degrees Celsius or much higher. J type thermocouple can also go to 750 degrees Celsius, but its lower side is quite high, 0 degrees Celsius. Just one issue with thermocouples we have to be careful of, which is known as the cold junction compensation. one end is kept at the position where we want the temperature measurement, but the other end also need to be maintained at a constant temperature, and that is why this second junction needs to be kept at a proper position. If it is open to atmosphere, we may have to go for some kind of compensation which is called the cold junction compensation. Generally most of the thermocouple sensing devices comes with an inbuilt cold junction compensation, but still this is an issue. I am not going into the detail of this one, but this is an issue you may have to be careful of while dealing with a raw thermocouple. Finally, there are a few laws of thermocouples, 5 laws basically, which we make use of while doing the reading. First is the law of homogeneous circuit. As long means suppose we are having two materials A and B, and the two junctions are kept at temperature T1 and T2. Now, our interest is only these two end temperatures. What are the intermediate temperatures? That does not matter. Like if the intermediate temperature is T3 or T7, it does not matter as long as the end temperatures are T1 and T2, that is sufficient, because you are going to get the same EMF as the output. So, all the intermediate temperatures in a homogeneous circuit does not matter at all. We are interested only at the two end temperatures, because the final output EMF will be proportional to that only. Second, law of dissimilar intermediate material. Like if any of the thermocouple is having another third metal included within this, then actually some suffixes are missing. Suppose this is kept at temperature T1 and T2, this is also at T1 and T2, and this is T3. As long as both the connections between this A and C, that is this particular connection and this particular connection, both are maintained at the same temperature T3, then the corresponding EMF will be the same. So, this provides a very useful way, while the first one provides that the first law of homogeneous circuit can provide that we can neglect any lead wire issue, and thermocouple wires can be quite long, exposed to the surrounding also. It does not matter if the temperature of the lead wire is equal to surrounding temperature. Whereas the second case, what we can do, we can easily cut in one portion from one of the thermocouples and incorporate a voltage measuring material, something like a voltmeter. So, as long as these two junctions are at the same temperature T3, then there will be no issue at all. Just an extension of the same thing, dissimilar metal at the junction. Instead of having something in between, if we put at one of the junction, as long as the connection between A and C and B and C are kept at the same temperature T2 in this case, then you are going to get the same reading, which is most commonly we keep on doing. This particular portion is kept at the location where you want the temperature measurement, and the other end we put the voltage measuring instrument, and we do not get any error in the reading. Fourth one, very important one, law of intermediate metals. Like if suppose two material A and C, let me do this corrections. I do not know why the suffixes are missing here. Suppose we are using a thermocouple comprising of metal A and C, and we are and they are maintained at temperatures T1 and T2, both junctions. Then whatever EMF we are getting, that is this much. Now we have another thermocouple comprising material C and B. Again the junctions are maintained at the same temperature T1 and T2, corresponding we are getting this EMF. Then if we make a thermocouple comprising of A and B, and they are kept at the same junction temperatures T1 and T2, then whatever we are going to get, that will be just addition of these two earlier EMFs. This is called the law of intermediate metals. This is a very important law from calibration purpose. It suggests that as we can use such kind of simple addition rules, it suggests that we do not have to separately calibrate each pair of thermocouples or each metal pair. Rather, we can thermocouple each metal with certain suitable reference, and then we can combine them suitably to get any kind of thermocouple combination. And just the other version of the same law of intermediate temperature. Suppose one thermocouple A and B, one thermocouple comprising of A and B is maintained at junction temperatures T1 and T2, correspondingly we are getting this much of EMF. Now the same thermocouple is maintained at junction temperature T2 and T3, we are getting this EMF. Then if the same thermocouple is maintained at junction temperature T1 and I am wrong here, In the first case, this thermocouple is maintained at junction temperature T1 and T3, and we are getting this EMF. Now, the same thermocouple is maintained at junction temperature T2 and T3, we are getting this EMF. Now, if we take the thermocouple and maintain junction temperature T1 and T2, then what EMF we are going to get? That is just addition of the earlier two thermocouples, which is called the law of intermediate temperature. This is again a very useful law from for the purpose of producing calibration charts or tables, where we can maintain one temperature as the reference ice point temperature and just keep on exposing it to some other temperature T1, T2, T3 or whatever, and whatever readings we are going to get, that generally are calibrated in suitable tables, and from simple addition rule like this law 5, we can get the value of EMF for any temperature combinations. So, these are about thermocouples. As the thermocouple output is low, quite often we combine several thermocouples into a pile, and which is called a thermopile, where another view of the same thing, like copper and iron combination is shown here. There are several beads created, all the beads or all combination of one junctions are maintained at one side, and other combination is kept at the other side, sometimes may be a suitable reference junction or isothermal block, and thereby we can get the simultaneous temperature measurement at different points, which is an application of thermocouple in the form of thermopile. We can sense small temperature differentials, and also we can amplify the output voltage if all the points are sensing the same voltage or same temperature difference. So, thermocouples we generally go for in this kind of application, where you are looking for small temperature differential over along a surface. So, that is it for thermocouples. That is where I would like to stop today also. Generally, there are 4 kinds of temperature measuring devices based on the change in electrical properties, but today we have discussed 3 of them: resistance temperature detector or RTD, thermistor and thermocouple. There is a 4th one based on the junction semiconductors that we shall be discussing in the next class. Till then, I am thanking you for your attention, and please wait till the next one. Thanks a lot.